Hello everyone, it's the final lecture in System on Chip Testing and Verification. It would be really nice to end this set of lectures with this final uh, slides or final lecture. I hope you learned something from this course. Uh, we have some news, I hope it's good. We will start with getting the grades of the project online. Then we will discuss much more about giving you quizzes online and maybe one assignment or two, then the final. So I will try to drop the assignments, but I'm really clear about the two quizzes so that all your grades are finalized. And it will be an online quiz and it will be simple, don't worry. Anyway, for the model checking, we were discussing this before. We're discussing that we have something called a property or a system property and a structure that we want to test on. Then we have a tool that's going to test this and give us either true or a counter example. The advantage of this is that if the system is true, we are positive that every single state is true. We are positive that the system is well tested 100%. And if it's not true, it will give you a counterexample where the error is. So this is a tougher way, but a way more smart than simulation because it's finalizing the whole process in a good check. Anyway, uh, building a model checker was a pretty challenging thing. Through this set of rules, I don't care a lot about them, but I'd like you to know them by just the names to remember something. You know why soon. That the problem was modeling CTL or combinational temporal logic in a deterministic way. People proved that it's complex and is p-space complete after all this rules. What's a p-space complete? Think about this. If I have a simple problem, usually it's linear. If it is not, it's non-linear, but less than polynomial. Then if it gets complicated, it will be polynomial. So the growth of the problem is related to n power 2, power 3, power whatever, which is the number of variables. So if I have two states, the problem will be n squared, which is 4. But if I have 5 states, the complexity will increase to n power 2, which is 5 power 2. Sorry, yes, which is 25. So the problem complicates fast. Then there is this NP hard problem. This NP hard is one of the complex ways or one of the complex problems that usually is hard for us to solve. You hear this in computer science a lot. You say, telling you it's an NP hard problem. But our problem is even harder than this. It's called p-space. What's a p-space? It's polynomial in space. So as soon as one state increases, the number of states or the number of states needs to be represented in the system increases by a polynomial form. For instance, if I have 5 states, I need 25 spaces in the net on the computer. But if I have 6 spaces, I'll go for 36. And take care, this is just a squared. Polynomial might be power 3, power 5, power 10, but at the end it's a polynomial. The problem of this is that it increases the number of states or the number of space we need on the computer increases heavily as things develop. Anyway, what we do is that we have an original algorithm described uh, by Clark in 1983, which it's called the fixed point algorithm. This algorithm uh, converts the whole p-space part to a non-linear operation of based on based on some conversion, which we will do. Anyway, we are based on this fixed point calculation, the algorithm uh, called symbolic model checking or symbolic fixed point algorithm. The symbolic evaluations allow us to enumerate the states and decrease the complexity. How we do so, let's think about it like this. First, what we need to do or what we need to recall that this is the kind of formulas we got: ex of p, eg of p, e of p, uh, uh, until Q, and so on. If we have an E, usually processing these operators will take the number S, the uh, vectorial of S, which is S number of states plus number of transitions between states. This is the complexity. Polynomial is easy, we know them. Let's say how we are going to calculate Ex of B. If you want to calculate Ex of B, it's simple. I'm going to stand in every single state and see if the next state of it is B or not. So I'll stop here. S1. Does S1 contains B? Does any state next to S1 contains B? No. So Ex of B doesn't hold here. I will go for S2. S2, yes, because S3 contains B. Good. S3, yes, S4 contains B. S4, yes, S3 contains B. So this property holds here, holds here, holds here. Until now, this is simple. To do this, it's simple to do that for P until Q. Simple. I'll stand here. Next state. If this contains Q, it might have a B before. So yes, it's true. Here, no, because the next state doesn't contain B nor Q. Here, it's B, and I can find the next state, which is Q. So E of B until Q holds. And if I stand it here, E of B until Q holds, because I have to find the path with B all the way until Q. B, B, and Q. So it will hold here as well. If we go for EG of B, we'll find things a bit harder. Why? Because I will have to check that there is one path that will always be true. Here, here, there, this path. So this path holds, but this one doesn't hold. Anyway, if this is true for EG, it's very hard to prove it for AG. But we are going to use a very interesting rule. This is called a kind of recursive definition of the CTL properties. So if I said AG of B, this means that I have B now, and next step, all passes got AG of B true. It is like, I want the tree. Okay, no. I have a tree. Then I say, at the state I'm standing in now, B is true, and for the next state, all passes, AG of B is still true. Remember, this is the recursive definition. I just jumped one step forward. EG of B is the same. I have B now, and at least in one pass, EG of B is going to be true. AF of B is a bit different. AF of B is B now, right now, or AX of AF of B is true. For instance, if I might have B now, which will be okay true, or next time in all passes, AF of B is true. EF of B is the same. So please remember that we have and or in this state, and this is important. Don't memorize it. It's in the quiz or in the exam. I'll give it to you written. And if it is in a final, you will have it. The exam is open book. So if I said A of B or Q, it's either I have B or Q now, and AX of A of B or Q. If it is E, we can write it like this, or the E is outside. So I can say B or Q now, and EX next time, I will have E or E of B or Q ready. Okay, so what we're trying to do is that we are calculating a new image. Instead of working on the FSM or the crypto structure we know, we want to move this to another equivalence that will make things easier to us calculate. That will make symbolic model checker easier to calculate instead of building the whole tree because it's p-space complete. This is what is called crypto structure. It's exactly like an FSM. Yet in FSM we have initial state, we have input function, we have output functions. and we have relations. Here we drop this because I don't care about the input on this line. Anyway, if I have a path between 1 and 2, I have to make sure, I have to consider it taken. So I removed all the inputs. What represents the inputs now is the relation between 1 and 2. If I'm in state 1 and I'm jumping to state 2. I don't care about the initial state because I can start in any given state. Only I care is the states and its output, which makes this a more state machine. Whoever used this, whoever did this structure, called Kripke. He's a scientist, a German one. And then Kripke said, I'm going to remove the initial state, I'm going to remove the inputs, and I just care about the states and its outputs. So if I'm in state 1, B is true, and of course A and C is false. If I'm in state 2, A is true, and of course B and C is false, and so on. So I have output vocabulary, which is A, B, and C, set of states, set of transitions between these states, and set of labels. Whatever state is, whatever uh, output is true in every single state. If we develop this, this is a tree because I can say B, A, like 1, 2, 4, 2, 4, 2, 4, or 1, 4, 2, 4, 2, 4, or 1, 2, 3, 5, 5, 5, 5, or 1, 2, 3, 5, 1, 2, and so on. It's a tree. We can convert this easily to an endless tree. But I don't want to do this. This is a way better way to calculate on. What he did, he defined something called a least upper bound and the greatest lower bound. Least upper bound, mu phi, and mu phi and mu phi, which is the greatest upper bound. Before we go to this, let's give you a small idea about what we are going to do. We are going to have an image transfer. We are going to transfer all our logic operations to the set space. We all studied set, I guess, first preparatory or something, very young, seventh grade, as my son loves to say. And now, if I said B and Q, I can say this is a set of states where B is true, intersecting the set of states where Q is true. B or Q is a set of states that B is true, union the set of states that Q is true. If I said not B, it's S, which is all set of all states, minus set of B is true. The false will means phi, the fully true will means S. There is one operation I want you to remember. Please remember this by heart. AX of B is equal to not EX of not B. If I want to say I'm true now, this means that next time EX, I don't have not B, okay? Not B next time is not true, which means that next time will be B true, next time will be B true, and so on. So AX of B is equal to not EX of not B. فكر فيها. أنا دلوقتي true, next time will be true, and it's always true. So if I want to say AX of B, that in all given states B is true, I will say that it means that next time not B will never be true. I have no pass next time with false B. I can use this formulas to solve it easily. I can say S minus EX of S minus B. S minus B, which is not B, I calculate EX of this. Then not is S minus this set. Now, I'll tell you more about the least upper bound and the greatest lower bound. The least upper bound means that S in B means that Y in an upper bound of S, and for all that belongs to B, which is an upper bound of S. Don't care about this stupid definition. I will tell you, I will describe the least fixed point or the least upper bound, which is a mu. If I said EF of B is equal to B or EX of EF of B, This is the rule EF of B we just defined earlier. I will start with Y, and because this is OR, I will start with the smallest Y possible. What is the smallest Y we can start with? Simply, it's phi. I need the example, I'm sorry. Here, it's phi. Then I'll go and put phi in this equation. If this equation is true, EF of phi, which is EX of phi, will be phi. So B ordered with phi, it's B. So I'll say EF of B is equal to B. But is this true? We don't know. We will keep substituting this F of Y many times in the same equation until the equation is fixed. So what I will do, I will start with phi. Phi will generate B. B union EX of B will give something new, until I have the exact set that represents EF of B. How can I define the exact set? If I have two executions after each other, two iterations with the same value, then I fix. Things is fixed now. As soon as that my function fix, I know that this is the maximum I can reach. On the opposite, sorry, I will start with the opposite. I will start with the biggest one, which is the S, and I'll keep getting smaller until I reach EG of B. Let's see a nice example. Let's calculate EF of B for this equation. I start with a phi, then I will keep substituting in the same equation. Mu phi dot is equal to mu phi dot B or EX of Y. So the first time Y will be phi. Next time I will phi. Next time it will be B or EX of phi. Then B or EX of B or EX of phi, and so on. EX of phi is phi, so phi will be go as this. B or EX of phi is B. Then B or EX of phi is B or EX of B. B or EX of B or EX of B, and so on. I hope it's clear. But anyway, we'll start with phi. Then I will go for the first iteration, B or EX of phi. B is the set of states where B is true, S1 and S4. Union EX of phi, it's phi. Anything union phi is the same, S1, S4. I'll go for the second iteration, B or EX of whatever I got here. So S1, S4, union EX of S1, S4. Let's calculate this one. This is important. EX of S1. Who is going to lead me to S1? It's S3. Nothing but S3, so I write S3. Who is going to lead me for S4? Still S3. So it's union S3. So S1, S3, S4 is the new set I'm going to substitute in the next iteration. So I'm taking this and substitute it. S1, S4 union EX of S1, S3, S4. S1, S4 union. Who's going to lead me to S1 and S4? They are S3. Who's going to lead me to S3? It's S2 and S4. So I write it. I'll union and I got an S. It's a complete S. I can stop now. But just to calculate more, I made one extra step, which is the fourth iteration, and you will notice that S1, S2, S3, S4 is still the same. The function is fixed. So EF of B, I start with a B, it's get larger until I got EF of B. It doesn't have to be an S. It doesn't have to be an S. Please remember this. So let's see the opposite. Let's start with an S and keep substituting in functions, see how things develop. S, B or EX of S, B or EX of B or EX of S, and so on. We'll see this function. We will go for EG of B. So B or EX of S, B is 1, S1, S2, S3, S4. intersecting any and will be intersecting ex of s1, s2, s3, s4. It's still the same. Ex of s is s. Intersecting this, I'll find this only b. S1, S3, S4. So it's getting smaller. So let's try this again. B ANDed EX of this. S1, S3, S4 intersecting EX of S1, S3, S4. What's leading me to S1? Take care. What I'm doing now, I'm converting all operation to EX only because I know how to calculate EX. So it's easier for me. So S1 and S4 are read by S3. It's here. S3, it's S2 and S4. I wrote them here. Intersecting, you find S3 and S4. Can you notice that S1, S3, S4, this set is getting smaller. If I went through the third iteration, it gives me the same result, S3, S4. Hence, these two iterations are the same. And now our function is fixed. So I can say freely that S3, S4 are true for AG of B. Other states are not true for AG of B. These other states and this process can be named counterexample. This state, if you went through it, this function or this property is not going to be true. Any. What we are trying to do here is that we are trying to see which states in this structure is true for a given property and which state is not true. Our goal for a good property, it's good or it's true for any single system aspect. Anyway, what we did is first we take this structure, convert it to sets. Then we convert our sum equivalence for fixed point factorization. But before we do this, we move everything to build a new image for the system in the set space. So we converted AND to an OR, and OR and not, and so on, to set relations. And this set relations is totally different. Anyway, we converted the complex. This is the target, this is the main target. The complex P space complete tree that we have to traverse it to a fixed point computation, which we don't need to traverse it, but it's only relations between and or and between sets. What we do here, if you think about it, if it is a big system, iterations will increase. So we converted the P space, we converted the space into time. Instead of having a very big traversing tree, which will take space and time, we cut the space and we convert it to more iterations in time. I hope this was clear. Let's take a real example for what we did. Yes, a more complicated one. Okay. Let's see this Kripke structure, and I will try to calculate AG of A or C. It's simple. AG of B is mu of y dot B and AX of y. Okay, there is a famous rule that I respect and I want you to always remember. It's essential. AX of B is equal not EX of not B. Now let's calculate the property A or C. A is true here. A is true here and here. So it's 2 and 3. C is true here, here, and here. So A or C will be the set of A where A is true. It's 2 and 3. Union the set of C where C is true. It's 3, 4, 5. It will be 2, 3, 4, 5. This is my B. The first iteration, because it's an AG, remember if it is a mu, it's always start with an S. If you have and in the middle, you always start with S. If it is a nu, you will start with a phi. So we'll start with an S, S1, S2, S3, S4. The first iteration here will be 2, 3, 4, 5 intersecting S. EX of S is S, or AX of S is S. So the it's 1, 2, 3, 4, 5. Here's the S. The first iteration will give me 2, 3, 4, 5. It's a bit smaller. Then I will go for the second iteration. It's a 2, 3, 4, 5, intersecting AX of 2, 3, 4, 5. How can I calculate TX of 2, 3, 4, 5? It's simple. I'll go for this rule. AX of B is equal to not EX of not B. So it's simple. I'll go for not 2, 3, 4, 5, not 2, 3, 4, 5, which is 1, right? AX of 1, what's going to move me to 1? It's 5. Not 5, it's 1, 2, 3, 4. Intersecting, it's 2, 3, 4. Then I will go for the second iteration, 2, 3, 4, 5, intersecting AX of 2, 3, 4, 5. Not 2, 3, 4, 5 or 1 and 5, 2, 3, 4, sorry, or 1 and 5. 1 and 5, right? Then not 1 and 5, which one is here? 2, 3, 4. It's we want to not EX of not B. So not 2, 3, 4, it's 1 and 5. EX of 1 is 5. EX of 5 is 5. So not 5, it's 1, 2, 3, 4 again. And I will notice that 2, 3, 4 is the fixed solution we have. Hence, our states are correct. This is an example. I will leave you to solve it, but I will send you the solution online. I will send you the complete solution of this example. I have it actually online, so I will write it and I will send it to you. But please try to solve it first. I want to solve AG for A or B or C and AF of A and B. And please try to learn to write a lot on this fixed point because it's important. So, what's good and bad about model checking? Model checking is good. It's easy to automate. I'll discuss theorem proving right now. The bad, that if the system is too large or if the properties are too complicated, model checking cannot be applied because it will get still state explosion. The ugly about this is that it's very hard for you to define that property. Sometimes you define a property like this one, which is a property that will show errors that can never happen in our system. And if we try to cut the system, because usually systems get really large, when we try to cut them, we might miss some states like this. This is a true positive. This is a system. I try to approximate it here because I'm working in a model, not a real system. Then I drop this bug state. Or I under approximated the system. Then I'll find errors that can never occur. What I want to do is that I want to get these states inside without getting any of these states. This state is called false positive, as if you went for an examination or something and they give you something wrong. This is one of the methods for model checking, for system verification. There is another way to do this. It's called theorem proving. We will not study theorem proving, we will study just an idea, a glimpse about it, but I want you to know. What we are trying to do is that we are trying to do verification as we did in high school by writing proofs. This is very exciting. We are going to write a proof to prove that this arithmetic unit really works. What's the advantage of this? If we wrote this for variable n, it's always true. But here is the catch. The catch is that our higher order logic system, as we said, it's not complete. So writing this proof can be a little tricky. The idea, very simple, is to define number of axioms, which we respect and we know it's true, and some inference rules, some relations between them, to prove that the description implies the specification, and we establish this theorem. We have different types of logic, as we said. So if we worked with first order logic, we discussed this before, the first order logic is like the propositional logic, but it have two quantifiers, which is for all and there exists only. This logic is still deterministic and we can define everything on it. So I have predicates, which is formulas like B, uh, Q, B implies Q and so on. And I have two quantifier for all and there exist. In the first order logic, I can quantify only over variables. What if I want to quantify over functions? It's very simple. If I say it for all P of 0 and it for all n, P of n implies P of n plus 1, this implies for all n, P of n. You know what is this? This is induction. This is what we know as induction theorem. As soon as we write this function, this is a mathematical induction, we all know it. We can never express it in first order logic. Why? Because we have a quantifier over P. And this is the whole catch of higher order logic. Because as soon as you have quantifier over P, you might get something like this. It's called the Russell paradox. B of Q is not equal not Q of Q. So if I substitute B by Q, then I will say P of P is not equal P of P. Doesn't make any sense. But Gödel in 1931 proves that there is no complete deduction system for second order logic and above. So because we are using higher order logic and we have to quantify over formulas, over expressions, we can never say that our mathematical model is complete. Why would I care? Okay, I care so much because algorithm guys work with complete systems. If you want to automate the system completely, your definitions or your mathematical model should be complete. Hence, higher order logic cannot, and I'm clear, be totally automated. We don't throw it away. I know it's not totally automated, but what we can do simply is to uh, use interactive models, which human beings have to interact with the system. This is another example. We always say C of t. Then when we use to write this, we say C of t and C of t plus 1 and so on. But now we can write all of this in one equation, which is very clear. Anyway, there is some tools that using us to interact with to solve this. I'll talk about two famous tools, like Palmore and Lambda are most of are some famous ones, but the biggest ones in the market, and both of them are free. Higher order logic, which is built by Cambridge, and BVS, which is built by I guess Carnegie Mellon or MIT. I can't recall it. Anyway, I like this formula. This is why we don't study higher order logic in details. PVS is a large and complex system. It takes a long time to learn to use it effectively. You should be prepared to invest 6 months to become a moderately skilled user. Yes, using higher order logic solutions or theorem proving systems take a huge time. This is why we just concentrated on a very small glimpse or a very small idea about what you're studying. Hull was built by University of Cambridge. I used this tool in my master's and I hate it. Yes, this is just like, and it's recorded. I'm not just saying it. It's recorded. I hate it. My first step when people ask me, "Are you going to do PhD?" Yes, but I'm not going to use Hull anymore. But anyway, Hull defines something called tactics and 8 primitive inference rules only. These 8 primitives inference rules are your axioms or what you are famous or what you are sure they are. Then I keep rewriting until I reach or prove my theorem. The idea is simple. I have a theorem which is known and I keep developing until I reach the theorem I want to prove. But in higher order logic, you were the first people to provide something called backward proof or goal directed proof. I will start with the theorem I want to prove as if it's true. And I'll say, okay, if I want to prove this theorem, what should I do? I should prove X. then what should I do? I should prove y, and so on, until I reach theorems that is known or axioms to me. So this is how backward proof happens. I have a theorem I want to prove, then I keep working until I reach two axioms I'm positive from. Let's think about forward proof ones and backward proof ones. If I want to prove an AND gate to be an AND and not, the AND specification is an output of I1 and I2. The NAND specification is an output of not I1 and I2. The NOT specification is the output of not I. And I will define the implementation of I1, I2, and that there exists an X where NAND I1, I2 of X ended with not X and output. So this is considered a signal. This is an AND implementation. This is a NOT implementation. What I'm trying to prove that for all given inputs and outputs, I1 and I2, this AND implementation implies the AND specification. This is simple. What I will do is that I will get the AND implementation and first rewrite it or write. Then I will strip for all X and I concentrate on this now. I strip therefore exists. Then I will rewrite the NAND. Say NAND is X is equal to not I1 and I2. Not is equal to this definition. Then I'm going to substitute the X here by the X in here. So the output will be not I1 and I2. If I have a theorem to simplify not of t is equal to t, then output is equal to I1 and I2, which is the AND. Quite easy done. The AND implementation implies the AND specification. This can be moderately automated and you have to do it by hand. But what if I have an inductive proof? Why I'm concentrating on induction? Anyone knows? Okay, let's move on and I'll tell you. If you want to remember induction, this is how it is. I have a basic case, I have an inductive hypothesis, and I have an inductive step. So for instance, if I want to prove that sigma of for I from 1 to n of I is equal to n multiplied n plus 1 over 2. I will have the basic case where n is 1. So I will substitute n as 1 and it turns to be 1, which is true. And I will give a hypothesis now. What's the hypothesis? That if n is equal to b, this is true. If I from 1 to b of I, sigma of 1 to b of I is equal to b multiplied by b plus 1 over 2. Then I will, if I could prove that if this hypothesis is true, this is true, I from 1 to b plus 1, I of b plus 1 multiplied b plus 1 over 2 is true, then it's true for 1, it's true for 2, it's true for 3, it's true for infinite n. I prove that this is true for any value of n. For any value of n. Let's prove the adder circuit. Not to prove it, just to show you how we're going to write the proof. I'm going to have an n adder specification, which is n number of bits in 1, in 2, C in, sum, and C out. And I can say simply that the adder specification is in1 plus in2 plus Cin is equal to 2 power n plus 1 multiplied C out plus sum. The sum plus a C out signal, which is one step forward than the sum, which is 2 power n plus 1. This is the adder specification. This is the ripple adder implementation we all know and we all good at. So it's simple. It is one bit adder connected to the other, connected to the other until n. Okay. I want you to remember very important aspect here. I'm proving this for n bit adder. I'm proving this for n bit adder. Nothing at all, no other proof system other than the higher order logic can prove a generic circuit like this. A generic means that n is undefined. Why? Because if I prove this, I can prove this, that this specification is true for any given implementation that looks like this forever, no matter how large your n. So I can prove it for a 16-bit adder, a 32-bit adder, a 64-bit adder, and so on. Anyway, let's think about our recursive definition. And I'm sorry, this looks complicated. I'll say that the n adder implementation, that there exists a w or an x or anything where it's an n adder implementation of n minus 1 and an n adder implementation of 1. The n adder implementation of 1 is the adder that we know. But there is a catch here, because when I write n1, it's from 0 to n minus 1. But when I write in the specification n, it's an integer. So I have to have a function that links n1 as a bit vector to n1 as an integer. So I define two new functions which called vn. Vn relate bit vectors to natural number or to integers. So if I say vn of 0 is bn of 0, bn is related one bit together. Our concentrator vn of x of 0 and n, this is equal to 2 power n multiplied b of n, which is the bit value of x of n, plus v of n of x of 0 to n minus 1. If I keep to do this, it's like converting. This is exactly, if I have like 4-bit 0, 1, 1, 1, I'll say 0 multiplied 2 power 0, 1 multiplied 2 power 1, 2 multiplied 2 power, plus 0 multiplied 2 power 2, plus 1 multiplied 2 power 3. This is exactly what I'm doing. I'm converting the bit vector to natural number. Using this, I will have to write my simple proof goal. This is my proof goal. For all n in 1, in 2, C in, sum, and C out, n adder will be implementation will be n input in 1 into C in and sum, C out implies n adder specifications, which is n v in, which is a conversion of this bit vector to natural number, vn of n2, vn of cn, vn of sum, and vn of c out. If I initiated n of 32, I'll just convert every n here to 30, from 0 to 31 or 32. But if I want to work with an n, it's possible because it's an induction. We do this like before for induction. So this is my basic stack. And yes, this paragraph is just my induction step. Is that if this basic step is true, this implies, if this basic step, no, this is induction step. If this is true, the implementation of n implies the specification of n, then the whole thing implies that the implementation of n plus 1 implies the specification of n1. I'm not asking you to prove it anyway, but this is what Intel is using since the error or the problem with the division bug we saw in the beginning of the course. The idea is as follows. If I want to prove a mathematical circuit or a computer arithmetic circuit, this is the best way to go. This is why, okay, I don't like to talk about myself a lot, but this is why we had to prove, or this is how we prove the exponential function used in the Intel Xeon processor using this higher order logic. Because now Intel can substitute n with 32, n with 64, n with 128, and it will still work well for the tank operation, and they can still calculate the error even before they build the circuit. So the advantage of theorem proving is higher abstraction and expressive notation between, this is how we prove airplanes will work always fine, ATM machines, nuclear reactors, not just the mathematics in the nuclear reactor, but also, or in the ATM machine, but also the interaction between you and the reactor or the ATM machine, so that they give you the card first before the money, so you don't forget your card. You cannot make any mistake in the past. You cannot stick them. You have to be moving in one single path, which is correct in the reactor or in the planes. So even human error can be modeled using theorem proving. This is the master of proving. So it's powerful logic reasoning. It can exploit hierarchy and regularity and so on. It's an interactive. I have very bad night to prove that A plus B multiplied by C implies B multiplied by C plus A. And to prove this, it took me like 8 hours or something for the first time I was learning it. So it's very tough. Large human investment to prove small theorems in the beginning, unusable only by experts, and requires deep understanding for design and higher order logic. You cannot work while you not know your design perfectly. Okay, but if people are like this, thinking will be tough. What happened is that we're trying to put things together, like theorem proving and model checking. How? It's called hyper verification. What we do is that we define the proof or the theorem using theorem proving. Then we keep divided to smaller goals. This is a backward goal division we know, until these smaller goals, these sub goals can be proven by model checking. And I'll throw these sub goals provable by model checking to the tool that can prove them and return them to me. Then I will keep adding them until I reach my primary goal. Some other people add simulation or emulation to the rule. How? It's something like this. What happens here, instead of just like trying to prove everything using formal methods or everything using simulation, I'll put them together. This is why they call it semi-formal. Semi here doesn't mean half formal, it means simulation plus formal. So it's semi-formal, simulation plus formal. We are using in here symbolic simulation or model checking to generate the variables that we need, to generate the corner cases that's not tested, and to see the result, to calculate the coverage we want and send them back to the simulation. So this is called semi-formal or smart simulation. What we're trying to do always is to calculate a bug, to find a bug. Please remember that 70% of your work, of the money in the field, are in verification and testing, 30% only in the design. But we are studying all our time design and we push all verification into a couple of lectures. One of my hopes is to have a theorem proving, or not theorem proving, for a complete verification system. Dijkstra once said that a formula worth 1,000 words. Anyway, thanks a lot. I hope this ends your semester in a good shape. We learned an introduction to embedded system very shortly, system on chip design flow, abstraction levels, which is transaction level modeling, model of computation. We learned system C and C++, partitioning techniques, communication and the schedule design, system on chip testing and verification. We'd like to learn more of the network and chip. Intellectual property protection, if you have a design and want other people to use. I have a nice lecture about this. I can share it with you if you wish. And heterogeneous system design. Here, we don't mean for heterogeneous, this can be a big course itself. Instead of using software and hardware only, what if we added analog systems or electromagnetic systems to system? And this can be a very hot system, which you have a chip with an electromagnetic part, like an antenna, on-chip antenna, or on-chip very high frequency circuit running with a processor, for instance, on the same chip. Thanks a lot and have a great day. Hope you're going to graduate soon and good luck.